darkest, clearest nights, there spills across the sky a milky ribbon of light. It is, in fact, our inside edge-on view of a galaxy. Discovery of our place inside this swirling complex of stars revealed a universe far different than we had ever imagined.
You're here on the surface of the Earth looking out through this Milky Way. You're looking at it edge-on as it goes overhead, and you see it as a great circle in the sky. And that tells you that you're in the plane of the galaxy, in the plane of this spiral galaxy that we live in.
It's hard for us to know exactly what our galaxy looks like, the Milky Way, because we're in it. And there's a dust layer in the plane of the galaxy that obscures our view of much of it. So we have to use radio astronomy, and we have to use some clever techniques that allow us to look above and below the plane, and we piece together this information to get a global view of what we think our galaxy really looks like.
Because we're curious, as all humans are, about the nature of the world around us, and ultimately in our place in the grand scheme of all things. Nature gives us this wide variety of problems that inevitably cry out for answers.
The first step in our understanding of our location in the universe came when William Herschel systematically counted the stars in different parts of the sky. Because most stars that he saw were concentrated evenly along the Milky Way, he correctly concluded that our solar system lies within a flattened disk of stars.
William Herschel, who had great intuition, felt, and accurately so, that we live in some kind of an aggregation of stars, what we today call the Milky Way galaxy. But he assumed that we were in the middle of it, and he attempted to map it without too much success. Very difficult to do.
Knowledge in astronomy has always been one that has tended to displace the Earth from being the center of the astronomical universe. Certainly the Copernican revolution displaced the Earth from the center, placing the sun in the center of a finite universe. Certainly William Herschel had an important part to play in his star gauges. But down to the 19th century and 20th century, beginning of the 20th century, the general idea still was that we were in a disk of stars somehow, and that there was a finite limit to that disk, but we were somehow at the center.
And we now know that this isn't actually the case. The problem that the observers were having was that they didn't fully appreciate the effects of dust in the Milky Way and how dust can block out the light from the distant stars. So that as people looked out from our location within the Milky Way, they saw the number of stars decreasing roughly equally in all directions simply because the dust was cutting out the light from the more distant stars. And this makes it very difficult to figure out where you are. It's a bit like being in Trafalgar Square in the fog and trying to figure out what London looks like. It's not an easy thing to do. So this really held up progress on understanding the shape of the Milky Way and our location within it for some time. It's actually ironic that the clue that eventually changed this picture was contained in Herschel's own observations back from the 1830s. The clue actually lies in the distribution of globular clusters around the sky, which Herschel measured.
The astronomer to make sense of this clue was Harlow Shapley. By chance, he observed the type of star known as a Cepheid variable within the globular clusters.
Harlow Shapley worked here at Mount Wilson Observatory with the 100-inch telescope, the beginning part of the 20th century. Shapley looked at globular clusters, which we know now today to be conglomerations of several 100,000 stars. And they're very old stars that orbit around basically the center of the galaxy, but not in the plane where the Earth orbits around the galaxy, but in sort of a halo surrounding the bulge of the galaxy. Shapley found in one of the globular clusters a variable star, a star that pulsates.
Cepheid variables are stars that are observed to vary in brightness with time. And the period of this variation ranges from about 1 to 50 days. These stars are all relatively more massive than the Sun, 5 to 10 times as massive as the Sun. But what's especially remarkable about them is that there turns out to be a very simple and tight relationship between the period of their variation and their luminosity. This makes them very useful for determining distances.
One of the contributors to our knowledge about Cepheid variable stars was Henrietta Swan Leavitt, and she discovered that of the Cepheid variables in the Magellanic Clouds, the brighter the Cepheid variable star, the longer its period of variability, the longer it took to go as it cycled from faint to bright to faint again. And that turned out, because all the stars in the Magellanic Clouds are essentially at the same distance from us, that meant that any change in the apparent brightness was related to a change in the intrinsic brightness of the star. The importance of that is that if you know how bright a star looks to you, and you know how bright it really is, then you can get the distance to that star. And Cepheids have turned out to be one of the most fundamental tools of calculating distances, especially very long distances.
Harlow Shapley used pulsating variable stars to determine the distance to globular clusters. He could count about 100 of them or so, and he knew that they were distributed in space around the center of the brightest portion of the Milky Way. Using this variable star technique, he got the distances to the globular clusters and therefore got the distance to their center of distribution, and he claimed that was the center of our galaxy. He therefore displaced the Sun, the solar system, the Earth, and mankind from the center of the universe.
Up until this point, the Milky Way was believed to be maybe a few thousand light years across. Again, the problem was the attenuation caused by the dust. The Milky Way seemed to sort of run out of stars, whereas in fact what was happening was that you just couldn't see them because of the obscuring dust. Shapley actually concluded that the Milky Way was more like 300,000 light years across, a great deal bigger. Now, Shapley had the galaxy about twice as big as it's now believed to be, but the idea that the solar system is offset from the center in a rather unexciting part of the Milky Way, and that the globular clusters form a sort of a wonderful distribution around the Milky Way galaxy is now pretty much the model that we have for our own galaxy.
But being Shapley, he then went on to imagine that the Milky Way galaxy must be the whole universe. And he began to argue against any theory that maintained that there were other galaxies. So where Herschel placed us in the center of the Milky Way galaxy, and Shapley had displaced us from that center, Shapley in turn put the galaxy at the center of the universe. Indeed, he made the Milky Way galaxy into what he called his big galaxy model, into a kind of universe of its own. And the spiral nebulae, which we now know today are other galaxies comparable to our own, in Shapley's view were demoted to smaller objects that occupied the halo around the Milky Way. So as often happens with a first-rate scientist or first-rate thinker in any field, with Shapley you had a great accomplishment and an enormous error almost at the same time.
Once we knew the basic shape of our galaxy was a disk of stars with a central bulge and a sparse halo of stars that extends far above the plane of the disk, we were able to ask the most fundamental scientific question: why? An important part of the answer came from a German-American astronomer.
A lot of scientists during the Second World War did research on weapons of various types or did other military research. Walter Baade, who was a very famous astronomer working in this country, but who had originally come from Germany, was prevented from doing war research. Because he was a German citizen originally, he was not allowed to do that. And so he got all of the telescope time while all the astronomers were busy. And so he went up to Mount Wilson outside of Los Angeles, and the skies were unusually dark because of the blackouts in Los Angeles. So he had superb observing conditions.
Walter Baade was instrumental in finding out that our galaxy is composed basically of two kinds of populations of stars, as we call them, blue stars and red stars. The blue stars are younger and expend their internal energy quicker, evolve away, and disappear. The red stars are very much older. He found that the distribution of these stars was different. The red stars could exist in a halo around the bulge of the galaxy. The blue stars existed in a very narrow plane spinning around the galaxy. This concept of two populations is critical to making theories of how the galaxy formed.
There's the first generations of stars, which we call population 2 stars. And these stars were formed, typically 13 to 15 billion years ago. And they're almost pure hydrogen and helium and only with a tiny content of heavier elements. And then more recently, what we call population 1 was formed, and that's richer in the heavy elements.
The abundances of the heavy elements in stars depends very much on how recently they've been formed. We know at the start of the universe, when the Big Bang occurred, the universe was filled with hydrogen. The only way that we get heavier elements in the universe is they have to be formed in the interiors of stars. And so if we see stars that are almost all hydrogen and helium, they must be stars that are made out of the original material out of which the universe formed. To have heavy elements present, it means that these stars are made out of second or third generation of elements. So what happens is the earliest stars form, evolve, explode as supernovae, and the heavy elements that were built up in their interior when the hydrogen and helium were burned are then spewed out into the universe and later form into new stars. The nearby stars, the ones that lie in the plane of the Milky Way galaxy, seem to be similar to the Sun and their chemical composition. But those that reach great heights above the plane of our Milky Way seem to be very poor in heavy elements. And we believe that those are the first stars that were formed in the galaxy.
The galactic halo is clearly composed of stars that on the average are much older than the stars we see in the galactic disk. And this fits in with ideas about how the galaxy came into existence. After you have the Big Bang and the material that must have come out of the Big Bang, and now you start forming galaxies and clusters of galaxies and all these things that are talked about in the cosmological theories, clearly you begin to form our own galaxy.
The classical scenario for the formation of a spiral galaxy like the Milky Way is that the galaxy collapsed to be something like what we see today in a period of something on the order of 1 billion years. This initially rotating cloud of gas, which would become the Milky Way galaxy, began to condense during the epoch of galaxy formation. As it condensed, the stars in the spherical halo of our galaxy began to form. These stars would be the oldest stars and would include the globular clusters, of which there are about 100 distributed through the halo of the galaxy. The halo stars, as they form, will continue to have the characteristic motions of the gas cloud at that time. But as the gas cloud continues to collapse, the rotation of the galaxy will cause it to collapse not in spherical fashion, but rather to collapse down into a disk.
And so when we look at the globular clusters and the stars in the galactic halo, we're just looking at the remains, the fossil remnants of the early formation of the galaxy.
We think the Milky Way is a very normal-looking spiral galaxy. If we could fly into a rocket ship out of the plane and look down, we would see a flat disk that's rotating, full of stars and gas clouds and dark dust clouds. Each piece in circular orbit about the center. For example, it takes the sun about 250 million years. That's a galactic year where we are, for the galaxy to rotate. Our galaxy has rotated about 60 times over the age of the universe. So in its own years, our galaxy is 60 years old, only 60 years old.
Today we know the basic size and shape of our Milky Way galaxy. Amazingly, we were able to learn this even though intervening dust and gas known as the interstellar medium, hide most of the galaxy from the view of ordinary telescopes.
Really, the part of the galaxy that we can see, even with the largest telescopes we have now, is a small bubble of the galaxy. It's just a corner of the galaxy that we can see with ordinary optical telescopes because of this dust screening our view. For instance, with the biggest telescopes that we have now, you could see a star with the luminosity of the sun all the way to the center of the galaxy. But because of the dust, you can only see actually about 1/5 that far. You can see to infinity in the other direction. If you look away from the Milky Way, you can see all the way out into extragalactic space and see other galaxies, and you can't see them if you look along the Milky Way. You can't see any neighboring galaxies if they happen to be in the direction of the Milky Way from our point of view, but you can see them easily if they're perpendicular to that.
Ironically, some of the material that obscures our optical view of the galaxy reveals its overall structure at radio wavelengths. Radio waves can penetrate what visible light cannot.
The primary information gathered about interstellar matter with radio telescopes has been the study of neutral hydrogen, that is to say, the basic hydrogen atom. It radiates a radio wave at just one wavelength, one spectral line at 21 centimeters, which is totally unique. You cannot confuse it with anything else. And radio telescopes the world over have been used to map the hydrogen gas by studying the 21 centimeter line.
The discovery of the 21 centimeter hydrogen line was of fundamental importance also in radio astronomy because it serves as a very nice tracer of the spiral structure in our galaxy and others. Being in the middle of the Milky Way, it's very hard to know what our galaxy looks like. In fact, it's easier to look at other spiral galaxies and from analogy infer what our own Milky Way looks like. But with the neutral hydrogen that can be probed with the 21 centimeter line, we really definitively, beginning in the 50s and 60s, saw that our own galaxy contains a spiral structure.
Indeed, we find that there are places in the galaxy that there is more 21 centimeter emission or more neutral hydrogen than other places, and it corresponds very well with the locations of the spiral arms. If you assume the gas, the neutral hydrogen, rotates around the galaxy in a uniform way, the way the stars do, the way we observe the gas and stars to do in external galaxies, then every velocity corresponds to a specific distance. You know just what that velocity should be at a specific place, because you can just imagine what it might be like on a flatly rotating disk, for example. So you're able to, just by looking at its velocity, understand where in the galaxy that gas is.
And as a result, we've been able to construct maps of the three-dimensional structure of the Milky Way galaxy, for example, how it rotates, where the spiral arms are, because in terms of interpreting the structure of the Milky Way, we are in fact in the worst possible position to study it because we're right in it. The hydrogen enables us to get a sort of a perspective and to make maps of what it would look like as if you were outside the Milky Way.
While it's clear that our Milky Way galaxy has spiral arms, less clear is what defines and maintains their shape over long time spans.
Now, why does it have arms? Well, that's a trickier question, but there seem to be instabilities that one can work out theoretically. It says, well, the material, as it goes around, can contract somewhat into arms. These are rather irregular arms, and some galaxies are more perfect than others in being nice and symmetric, some are not. It's a kind of a random process, and that's not one we understand well, but we think perhaps we understand it roughly.
For example, we know that as you go out away from the center of the galaxy in the disk, the speeds with which stars go around the center of the galaxy changes. And you expect what's going to happen then is that the galaxy will wind up. That is, the inner part tends to want to go around faster than the outer part. And you would expect that if the spiral arms followed that spiral arms would just wind up after a while. That apparently does not happen when we compare our galaxy with other galaxies of similar types. So there must be some explanation for the tendency for spiral structure to remain fairly permanent
Astronomers, including C.C. Lin, who was my advisor, and others, came to the view that spiral arms were actually a wave phenomenon, much as a traffic jam is a wave phenomenon. The pattern as a whole, which is the spiral pattern, need not wrap up in that situation. For example, the pattern can rotate rigidly as a solid body, so a billion years from now it looks more or less the same. But the individual stars, which are moving at different speeds, move through this just as the cars move through a traffic jam. So spiral structure in some sense is a traffic jam in a galaxy.
We believe that spiral arms are basically density waves moving through the stars and gas present in a galaxy like the Milky Way, just exactly as the sound waves that carry my voice are density waves moving through the air. Now, in the gas in particular, as the material in the galaxy moves through this density wave, molecular clouds or regions which are going to become star-forming regions, as they enter the density wave, will be compressed. That can cause a shock wave to reverberate into the molecular cloud and can stimulate the star formation, which we see to be present in the spiral arms. As a result, the spiral arm, the spiral density wave, stimulates star formation. New young stars turn on. Those luminous stars are very easy to pinpoint, and they delineate the optical spiral structure which we see on all of the beautiful photographs.
When you look at external galaxies, you see a distribution of bright spots, bright stars that follow these spiral arms. The spaces in between the spiral arms are not devoid of stars. There are plenty of stars there, but the regions along the spiral arms are the regions where hot, young, newly formed clusters of stars are located. Stars are formed in clusters in the spiral arms. So it's just that these bright, young, hot stars delineate the spiral pattern and highlight them, so to speak. Our galaxy is probably just like that. We have evidence from looking at the distribution of our own hot, young star clusters that they, too, fall in patterns in our galaxy that follow spiral structure.
And those clusters that are in the disk of the galaxy are open clusters. The reason for that is that the clusters that are in the disk of the galaxy generally have very much smaller masses than the globular clusters do. The numbers of stars are the order of hundreds or a few thousand. And so as a consequence, they're not so dense, and you don't have this sort of swarm of bees structure. And therefore, the terminology open just meant that they were more spread out.
The bulk of the mass of the galaxy is tied up in these stars, whether they're young star clusters distributed along the spiral arms or through the more numerous low-mass stars that are really distributed smoothly throughout the disk of the galaxy. And this disk is very thin. It has a what's called very high aspect ratio, very, very thin compared to its size. It's more extreme than the old 33 RPM vinyl records, if you can imagine what those were like. Very, very thin compared to its size. Our galaxy is just like that. Although it is not a completely flat disk, it also has some warps in it, as though you'd left that vinyl record out in the sun and it kind of got warped. That's what our galaxy's shape is like.
As intriguing as the spiral arms are, the real mystery lies at the center of the galaxy.
We've been studying the center of our galaxy now for some time, particularly with radio waves and with infrared. Why? That's because in the visible region, with visible light, you can't see the center of our galaxy. Astronomers have been stymied for a long time because of the dust clouds between us and the center. But with infrared and microwaves, we can get through and we can see the center. Now, what do we find there? Well, a lot of phenomena. Some are very puzzling.
When you get very close to the center of the galaxy, there's a galactic bulge, which is really just an extension of the halo. And we don't understand very much about that galactic bulge because there all the components of the galaxy come together. The halo, for its part, the thin disk of the galaxy, and the thick disk of the galaxy. They're all intertwined in that region. And trying to disentangle for any given star or group of stars in the central bulge of the galaxy which of these systems those stars belong to is a very, very difficult problem.
But we can see, for example, that the stars are moving faster and faster, going around the center faster and faster as we get closer. Also, gas is doing the same thing. The gas is circulating around. It gets faster and faster as we get closer. And that's a good signature or a sign that there is an enormous concentrated mass in the center. About 2 or 3 times the mass of the, 2 or 3 million times the mass of the sun is concentrated right there. Thought to be a black hole. We know of no other way of concentrating such mass. It must be a black hole there. And we've been studying, we can see various objects in there. There's one very peculiar object which might be the black hole, but we still have to look more and try to figure that out for sure.
So our galaxy, the Milky Way, still holds many mysteries, cloaked in the dust and gas of interstellar space and surrounded by a majestic whirlpool of hundreds of billions of stars. To divine the galactic core and other mysteries of the galaxy, astronomers turn their telescopes not just inward to the center of our galaxy, but away from the plane, to the countless galaxies that populate the infinite frontier.